Hello, everyone, and welcome to the Temporal Graph Learning Reading Group. This lovely Thursday, we have the pleasure of Sofiane Ennadir. He is at King AI Lab and received his Master of Science in Data Science from École Polytechnique in France and MNS UM6P in Morocco. I hope I didn't butcher that one. And now you're currently doing a PhD at KTH, Royal Institute of Technology in Sweden, under the supervision of Professor Michalis. Okay, I'm not gonna pronounce that last name. I'm gonna butcher that as well. But you're working on adversarial robustness in graph neural networks. You're a AI researcher at King AI Labs, Microsoft Gaming, where you work on representation learning in continuous time, dynamic graphs, and theoretical understanding of transformer-based models for different applications. That sounds very relevant for this reading group. So we're very happy to have you and take it away. And before you start your presentation, do you want questions during the presentation or afterwards, or?
No, please feel free to interrupt me if there is any question. I'm happy to answer at any time,
All right.
Either in the middle or at the end, as you wish.
Perfect.
Yeah, so thank you very much for the kind introduction. So yeah, in my PhD, I was working more on adversarial robustness for graphs. Then I kind of transitioned from that for my PhD to working for like a full-time for King AI Labs, which is kind of part of the bigger, let's say, picture of Microsoft Gaming. And what I will be presenting today is actually two works that we have done during my period here. One of them was published in Temporal as a survey, and the second one was published in a log conference, which took in December, if I remember, in Arizona. And that's the title of the talk, which is Virtual Nodes Go Temporal. So this was a collaboration with some awesome collaborators. The first one is Yassir Jedwa, who is now an assistant professor in Imperial College London. Before that, at the time of publication, he was a postdoc at MIT. And two of my colleagues here at King AI Labs, Oleg and Lily. So usually when we talk about graphs, we just think about kind of nodes, and we have some connection between them. And this can be represented by adjacency and node features, classical graph representation learning. And basically, towards the years that have been used for different stuff, including node classification. For instance, we want to know if one node is a spammer or not, something like graph classification, in which we want the whole label of the graph, and finally link prediction. And this is where I would say is the biggest application of graphs in industry, is that we basically look at the users, we see what they interacted with and what we want to expect, or at least what we want to do, is to predict accurately what will be the next action that they will do. Because if we can do that, we can propose it beforehand, and we have much more chances of them accomplishing this action. So not only it enhances the user experience, but it also gives us a leverage on what kind of things that we can recommend. And basically, we want from static graph, in which we consider that the adjacency is kind of static. It doesn't change throughout the time, to stuff like where we start with some nodes. And these nodes, during time, there will be some interaction. For instance, you can see it as I bought a new item, so I will have a new edge between them, or two other users interacted between them, etc. In some cases like ours, we can also have a new user that joins the group, so it will also update the overall graph. So why is this even relevant to us? So we work in the gaming industry. So in gaming, our users are players, and we have a lot of games and different actions that the users could do. For instance, I can play a level. I can either pass it or fail it. Or for instance, I can buy something like a reward, and I can either use it or just keep it or something like that. And in our log, we can look at this as what we call event stream. Is that it's just a dict in which we have some players, the actions that they did, the kind of, let's say, event that they interacted with, and when did this event happen. And we just track all of this during time. And historically, how that have been used is that we consider it as a time series, for instance, in which for each user we have a certain time series that reflect this kind of evolution during time. Or what we call event stream is basically a whole field of research in which they would take this kind of tuple or this dex, and they will try to interact it with transformer. The main problem here is that we consider the players, the events, and everything to be independent, which is not necessarily the case, right? Because if we have a user, for example, in Sweden, he probably have the same tendencies as people that are, for example, in Denmark or something like that. So by just considering it as independent without taking that aspect of the group, we lose some information. So that's where representing to the temporal graphs could be useful, is that we can consider that we have our players as a graph, and basically whenever I interact with a new event, I will have a new edge in my graph, and basically these are the couples. So basically here the nodes are the users, and also the items or the different levels with which I can interact. And when we talk about dynamic graphs, there are two main sides. The first one is what we call discrete graphs, is that this difference in terms of time. For instance, I know that an action will happen each day. Let's say, for instance, I send a formula to some users and they have to respond in time. I know that I will get this information every 1 day or something like that. In our case, it's a little bit different. It's what we call continuous graphs, is that I don't control when the users will play or will interact with the general environment. And that's why I can't actually track what is the difference between the two of them. This is more general. And actually, there was a paper that shows that any discrete graph can be seen as a continuous one, obviously. It's just going from something discrete to continuous. That's an easy way. Is the other way that is usually a little bit harder. So during all the talk and our work, we usually focus on continuous dynamic graphs. But it still applies to the discrete aspect. You can take the same insights there. So in static graph, we usually have message passing network. And the main idea is that my representation in a network depends on my friends, and their representation depends on their friends as well. And I do this in a certain aggregation, is that I will take all the information aggregated to me, and that will update my new representation. And usually we do it in a certain recursive way. So I see the friends of the friends of the friends, etc. And while one could be tempted somehow to put it to infinite, obviously, you will have the problem of oversquashing and oversmoothing, where everything will collapse into something like a similar vector of representation. So dynamic message passing is kind of similar from our understanding, is that rather than considering in the static graph that we have one neighborhood, we actually have something called the temporal neighborhood, which is basically all the nodes to which I have interacted during time. And I do the same kind of aggregation, either based on attention or something like mean aggregation or something like that. And that will give me a certain representation. And then I just update this node in the local level. And after that, I can have something like a memory state, which keep my representation during time. Because obviously I don't always get updated because I don't always interact with others. And that's why I need this kind of memory. Some other people have also added something called temporal projection, is that if I don't get updated, I still get an aspect of time. And that's very important. But then the same question that I said before regarding the oversmoothing also happens here. If I just put everything to infinite, I will have the same effect. So questions about how we can modelize long-range dependencies is very important. So how did we modelize everything? We wanted first to understand theoretically what's happening in this temporal message passing. And from that, we can see what is lacking, what is absent. And based on that, we can propose new stuff. So we propose something called the information flow. So the hypothesis is that when a user interacts with some action, so there's a new edge that happened in the graph. Ideally, I want this to be modelized in all the other nodes. So all the representation will be updated, and such I will have a better representation of my graph. And I can, for example, recommend more updated stuff. So we introduced this concept of information flow, is that given one graph at t equal to 0 and t equal to 1, so there's only an action that happened here, which is represented as an additional edge. We want to calculate the difference in terms of the representation between the two graphs. Once I go from this one to this one, I do message passing. Obviously, the node representation will change. And I just want to calculate this as a distance. And this distance can be anything. For example, in our case, we consider the L2 distance, but you can do something smarter, which is based on KL or something like that, to reflect more probabilistic aspect if you want. And basically check this in terms of expectation of what's happening in terms of the graph. So we introduce a definition based on a certain graph-based function, which can be based on init temporal message passing, that it is mu sigma flowing if basically this quantity here is smaller than a certain sigma. Obviously, what I would have wanted here is to have a lower bound. The problem there is that theoretically you can do it. It's really hard without some assumptions on how is the distribution of the nodes. So for the moment, we will settle for an upper bound. And the bigger this upper bound, the more expected is that this difference will be bigger, which means that this event had much more effect on my graph. So all the nodes have been well updated. Okay, so this is the first theorem based on this information flow in which we consider the temporal message passing. In this case, we consider that the aggregation is done as a GCN layer, which is based on the degrees of the neighborhood. And basically what we find is two main things. There are two specific cases, okay? So we consider that the event happened between node E and V, and we consider a certain node U that can be anywhere in the graph. What this theorem says is that if this U that we consider, the node that we consider is within a reachable distance, which depends on the number of message passing, then basically this function mu sigma is flowing, with sigma only dependent on the temporal projection, which means that the message passing didn't actually reach my node, which is kind of obvious, okay? The second case is that if my node is within the reach of the message passing, then the update depends on two main things. The temporal projection, obviously, because that's always happening, but also the difference in terms of the memory of the nodes in which the event have happened, okay? So how is this represented is that we see here that there is a certain term of work, which we consider the temporal work. What does it mean is that since it is a message passing and it is a kind of aggregation, let's say the event happened somewhere between here, then the difference or in the first hop, I only see the direct neighbors, which are directly updated in the first hop, but then in the second one, I also see the second one. And that's why I have this aspect of the message passing through the paths. So the more connected the graph, the more easier it is to propagate the information. Obviously, if it's not connected, then that's exactly what we say, okay? So depending on where I am in the graph and how am I situated towards the event or where the event happened, a node can be updated or not, okay? And similar insights can be also derived in the case in which we consider attention-based. So in the previous one, we have considered GCN-like aggregation, but if you consider, for example, attention-based, then basically, rather than having the works, you will have the degree. So it depends on how connected is the graph in terms of the degree of the nodes. The proof is available on the paper, and you can check it. It's not that hard, actually. It comes from the principle of Lipschitz continuity, and you just derive all the distances, and it will give you something like this. Okay, based on this, we can somehow, at least from our perspective, derive some insights on the general literature of temporal graphs, and that's where we presented in this paper, which is a kind of survey where we try to divide all the papers based on how they do the message passing. So basically, there are methods that do the message passing, the classical one. And within these, we have the memory-based and the non-memory based. So we know based on this theory that if you don't have the memory, then this difference is not big. It depends on the direct embedding. If you don't have the temporal projection, you know that any nodes within the graph that is not within reach of the message passing won't get updated. So based on this, basically we get this nice topography from which, depending on which use case we are considering. Let's say, for example, I have a graph which is really dense. So I know any nodes is within the message passing, then I don't really care about having a temporal projection or not, because I know that anyway, whenever an event happens, I know that the message passing can take care of that and will give me somehow an update. So it's having the temporal projection is nice. It just adds complexity. But in some cases in which I know that, for instance, my graph is kind of sparse and not all the nodes will reach, or not all the events will reach all the nodes, then maybe it's better to have something like a temporal projection. Okay. So obviously what we learned from the theory is that there is a kind of problem in the actual message passing, at least from our understanding, is that if there is an event happening between these two nodes here in red, then if I just choose a L equal to 1 as a message passing, I only see the direct neighbors and those for which the information would propagate. Okay, so basically based on this distance and the diagram of the graph, that's how the information will flow. If we take this example in Europe, for example, and we consider that Europe is all connected to a graph, if I just add use a L equal to 1, and let's say I'm in Sweden somehow, then I'm only connected somehow to the Nordic parts or something like Netherlands or something like that, or Germany. And that's kind of problematic in our case because the users could be connected to much further than the L hop or the L that we use. And in this case, we are limited and it doesn't really help. At the same time, we can't put L to infinite because we'll have to alpha smooth it. So that's where somehow virtual nodes could be interesting. And that's what we propose actually, is that we consider that we have some graphs and for each part of the graph, we add some, let's call them child nodes to which are connected to the smaller original nodes, and they are fully connected between them. So what happens is that when I have a new event here happening in red, then the direct message passing will obviously update my own community since I'm already within the L hop there. But at the same time, all the information from my community and my own information will go to the parent node. And this parent node, since it is connected with the any parent nodes that we have, then the information will propagate to that and then will go back to the other nodes. So by just adding two virtual nodes on top of these nodes, I can make the information from this part of the graph go to this side of the graph, which could be really useful in our case. Okay, so how can we theoretically show this is that, again, to the information flow, what we see is that actually, if we consider that we have the same propagation as, let's say, the first theorem that I showed based on GCN, then let's consider F to be the original TGN, for instance, and then J is a variant in which we added K virtual nodes. So it shouldn't be just 2, it can be K. And each node is connected to M node at max, okay? Because it depends on the communities and how we choose them. Then we know for certain that the information flow for any individual nodes, wherever it is within the graph, will have an extra term, which depends on the direct information between the two nodes, okay? So I know that the information that happened within that event will obviously get diluted because it depends on how you do the aggregation. Here we consider that we do like an average aggregation between the different communities. But if you have something like attention, it could be adaptable. So we know that the sigma prime will go higher, and that's very useful. So this is just theoretically showing that the information flow will go higher. Okay. Here we just look at the general framework of what we are presenting, is that if we look before on the TGN, if an event happened here in blue, then the updated nodes, which we denote here in red, are kind of limited. But if you use virtual nodes, for instance, what will happen is that all nodes will be somehow updated. How is this represented in reality is that you have your original adjacency matrix, and you just add some connections which represent the virtual nodes, okay? So you add k lines, for instance, and these are all connected to, these represent the new virtual nodes that you add here, and they are all connected to their correspondent child nodes. And obviously it's similar because it goes both ways. So I have to propagate the information this way, and then to the other way, and all of them are connected together. And that's why we have the one here. And so basically the algorithm looks something like this. I consider that I have a certain assignment function. So basically for each community, I have a function that will take this community and say, okay, this should be a community on its own that have this virtual node, and basically will assign one. And then we build the adjacency matrix, the new one, and we just do the new prediction and compute the loss. So it's a kind of similar classification as a TGN or something like that. So it's not that different. We only augment the adjacency matrix. And obviously here the assignment function could be anything. You can tell me, okay, how do I choose the community? Well, that's your choice. Take any algorithm that you like, or do something like random. We know for sure from a theoretical perspective that it will enhance the information flow. Now, it is crucial how we use this information, how we use this assignment, in the sense that imagine that I assign this tree here to the same community, to the same virtual node, and I assign this two here to the same virtual node. Since the message passing have already touched these two nodes, then I will just have a redundant information going to the virtual node. So typically what you want to do is that you want to go beyond your L message passing to something new that you haven't seen through the message passing. It just complements somehow the message passing part. Okay, so beyond this, there are two kind of criteria that you should choose for your assignment. First of all, it should be fast. Imagine that we have the best community detection algorithm that takes a higher complexity. If you just add it in the algorithm for each forward pass, it takes too much time and it will take an eternity to run. And you want it to be accurate, right? So it's a big trade-off here. I prefer to pay in terms of accuracy, but I would still have something that is fast. Okay, and there's a certain kind of theorem. It says that basically, if you have an adjacency matrix, if you just want to compare their two adjacencies and you want to have their maybe so let's say I have mu and v, which are two nodes within my graph. Basically, what this says is that comparing their direct representation in the singular space is comparable somehow to compare them within the adjacency matrix space. Okay, so if I consider that I already have my communities, which are usually denoted in the singular space, then basically it's similar to comparing directly in the adjacency matrix. This is just an easy way of introducing the key means algorithm. What it says that I can directly take my each line of the adjacency, consider it as somehow representation, and I do randomly my clusters. Then I start updating these clusters based on some certain distance, such as I have the best clusters. Classical k-mean algorithm, we do it in a certain iterative way until it converges. So after a number of epochs, which is t, I will have my communities, which is kind of fast, as I will show afterwards. Okay, so if we just apply this and then we look at the final representation of the model, here what I'm representing is pretty simple. I take F, which is the original TGN model, and I F augmented by a TVN. So here I added the virtual nodes, and I'm comparing the information flow of two of them. Remember that the information flow is simply the difference in terms of node impedance after an update. So I can do this empirically. I consider infinite number of nodes. I just resample. Here I didn't take all of them because it would take too much time. And I look at the difference between the two of them and then do the final difference in terms of information flow. And what we see in terms of this distribution is that actually in the majority of cases, the difference is positive, and it's kind of bigger than 0. It's pretty diverse, and that's why I said in the beginning, we only have an upper bound. We don't have a lower bound. If you manage to show that basically you have a certain lower bound, that's way better, because you can set here that I want the difference to be bigger than 5. Here, what I'm giving you as a guarantee is not as truthful as having a lower bound. That's what I'm saying. It could be technically 0, right? So that's possible, and it's still valid theoretically, but it didn't add anything in terms of reality. And then we go to obviously the important evaluation is that we just take the TGB, the temporal graph benchmark. We took a TGN, the classical one. We just augmented with our virtual nodes, and we see what will be the relative improvement here. And we see that in the majority of time, it can enhance the performance of the classical TVN. It still don't reach, obviously, the SOTA kind of model, but it's kind of okay-ish in terms of the time complexity that you will pay to get this kind of improvement, which is kind of good. We also see that there is a difference between the different, let's say, different data set that we consider. For example, here we have something like 40%, while in some other we have like 3%. And actually, if you just put the surprise index of these data sets, you will see that actually you are much more performant in the data that you don't have much surprise. Why is that? Is that because we do the communities based on the batch. So at each batch time, let's say 200 events, I will build my community to the k-means. So if it's too surprising, what will happen is that everything will collapse, and I don't have a really good communities. That's why the improvement is much more or less. That's at least my intuition. It doesn't mean that it was the case, but that's one way of explaining it from my point of view. Obviously, we also compare to something called TGR, which is basically they propose to do a rewiring to expander graphs. Please note here that these are based on our own implementation of TGR. From our understanding, there is a certain problem with what they published in terms of numbers, because there's some kind of leakage in the evaluation script. I don't know if they fixed it or not, but this is based on our own implementation. And we can see that in the majority of times, or in all of the times actually, the TVN outperformed the TGR, which is very interesting. Okay, we did some ablation studies here to understand more the different parameters and hyperparameters of the model and how they would affect the final, let's say, performance. In this specific case, we consider the number of clusters, because in k-means, you have to choose the number of clusters or the number of communities that we have in the graph. So we started from 2 until 10, for example, and we see that the performance is actually bigger when it's 2. This may be due to the fact that in the majority of the data sets that we consider, at least TGBL wiki here, it's kind of bipartite. So building a community that is bigger than 2 in a bipartite graph doesn't make sense. Maybe that's why it fails. But nonetheless, we can see some improvement over the original TGN, which is still very interesting. We also wanted to understand what is the number or the perfect number of iteration. If you remember, k-means is a kind of recursive model, and you do it for a number of iteration. And we have seen here that if you increase the number of iteration, it doesn't necessarily give you the best results. And somehow, like t equal to 10 would be okay-ish and would give you actually the best result. So that's why we consider that k-means converge really fast, and it's okay to be used. We also compared the k-means because, as I said, the assignment function can be anything basically. You can choose something like random, for instance. Here, we just take k equal to something, for example, 2, and we just assign randomly all the nodes, the child nodes, to their parents in a random fashion. And you can see that it also increased the performance over the original TGN, but it seems that the k-means somehow give the best results in terms of the downstream performance, because maybe it can get the best, let's say, communities. We can also compare in terms of time complexity here, where we consider a TGN, the virtual nodes, the Louvain. So one thing is good about Louvain is that you don't have to specify the number of clusters, and then the random assignment. And you can see that while VN is a little bit more complex than the random, obviously, it is still kind of comparable to the TGN. So you don't pay that much in terms of time complexity, but you gain much more in terms of downstream performance. And that goes back to what I was saying about how fast it is and how accurate it is, the two main criteria that we want. Obviously, you can choose some other more performant ways. Here we consider at each batch time that we have a kind of static graph, but you can consider something like a temporal clustering, in which you can use the final state of each of the graph from the temporal message passing, and you can do your own communities. That will probably be much more wiser than just doing a classical k-means, I would say, and maybe it will give better performance. We didn't try this, but we got it from some comments from the reviewers and from the poster session, and I thought it would be a nice extension of this work. Okay, so just to conclude, modelizing long-range dependencies within TGN is kind of challenging. It's a very interesting subject. From my understanding, there are some works that worked on that part, but it's still, in my opinion, a kind of open subject that is still to be solved. And in this perspective, virtual nodes can enhance the information flow and could consequently help in this overall modelizing of long range. So you can find, obviously, the paper here through this QR code. The code is public in GitHub and can be directly used. And this paper was presented in the LOG conference this year. Yeah, so that will be all from my side, and happy to take any questions.
Thank you so much. I think I saw a raised hand. Sebastian has a question.
Yeah. Thank you for the talk, Sofiane. It was great. Potentially naive question here. I'm just curious, is there a reason it's significantly harder to prove a lower bound for this?
At least I don't know how to do it.
Okay.
So based on me, it's harder. But it doesn't mean that it's harder absolutely. I come from a background of Lipschitz continuity, and I can tell you that all the works that have been done before couldn't do a lower bound. In my opinion, to do that, you will have somehow to consider something about this distribution of the nodes, which then limits you to your specific. Let's say, for example, you have something like a SVM graph, like stochastic block models. Then you can, in this case, for example, prove that there is a lower bound, but it doesn't mean technically that it can extend to any graph. So for the generality, it's way easier to go to a lower, an upper bound. It doesn't give you the guarantees, but at least it gives you a kind of expected value. That's our opinion.
Gotcha. Okay.
But if you manage to do that, I would be really interested to read it at least. Yeah.
I think I also have a question. So first of all, I want to say I really love your slides. I know it's cheesy, but the figures are really nice. How does this method change the computational complexity? Does it make your algorithm much slower than the others? Because I would imagine that when you introduce these virtual nodes, then it changes the message passing, and maybe the neighborhoods explode or something like that. So
yeah. So based on the experiments, at least in terms of time complexity, it didn't add that much. It's something like 2 seconds. Obviously, when you go to bigger graphs, it will be much more complex. Here, I only show 2 TGB wiki. If I remember, in the case in which you do, for example, flight, it usually takes around 8 hours for the classical TGN. If you add this one, it will be something like 10 hours or something like that. So it gets a little bit higher. Uh, uh, so in terms of the algorithm, it's how you do the assignment. So just to compare, for example, to TGR, which they do the rewiring, you pay the price in the beginning of the code because you create your expander graph, and afterward you already have the communication, so you just take the whole adjacency. In our case, for each batch, you have to recompute the communities. So it depends on which assignment you are using, the assignment function that you are using. If you use something too complex, then probably you will pay much more time. But you will gain in terms of downstream accuracy. In our case, it was okay because we usually do a recommendation before. Once you have the embeddings, you can directly do different matching in terms of cosine, so it's not a problem. So it was more offline problem, and that's okay to do it, I think.
Nice. Thank you.
Yeah, no worries.
Are there any other questions? You can also write them in the chat, then I can read them out loud. Otherwise, I can shoot another one.
Yeah, sure.
So this work, is this something that you have taken into production or that you're using for some real world, use cases in your work, or is this just for the TGB examples that you've outlined?
Yeah, for the virtual nodes, we are still in the process of making it work in terms of applied, but at least from the graph side, we did it for like some small use cases to build the graph and everything, and it works pretty well. So hopefully this virtual nodes can also go into the pipeline eventually.
Okay.
That's what I would hope. From my experience, it's a little bit harder. I mean, when you work with TGB or something like that, you already have the graph, you already have the loaders and stuff, so it's way easier. But when you go to the going from this, let me show it again, from this event stream stuff to the graph part, it's a little bit more tougher.
Yeah.
How you choose everything, how you do the delay between everything, especially if you have a huge number of users, it usually just go out of hand. And how you do the batching. And actually, one possibility that I didn't yet work on for the virtual nodes, when you do temporal graph, you have this kind of batching, and basically you update the memory, but you lose all the information between the two of them, right? Between a batch and the other. One way of using the virtual nodes, not through the adjacency, but actually through the batch. You could imagine that all the batches have a certain virtual node. So each batch have its node, and all the batches communicate between them. And you just do something like attention, and you have a way better way of doing batching than just doing the final aggregation. That could be an interesting extension of what here we have done it in the log. Let's say in the log at each batch, but you can consider that all the batches are also connected, and you can make it to work. And you can easily show from an information flow perspective that this could be a little bit better.
Super cool. Thank you.
Yeah, thank you very much. Yeah, and if anyone have any question either now or afterwards, please feel free to contact me. I'm always happy to talk about graphs and answer questions.
Quick follow-up to that discussion.
Yeah.
So you can think of the virtual node as sort of like a representation of the entire batch or the entire graph. So it's sort of like analogous to like a CLS token at the beginning of like a tokenization representation of a sentence or something like that. So I'm curious if is there literature out there that proves a similar bound on information flow in the context of language models or anything like that with a CLS token?
For a language model, I don't know. At least for the temporal graph, I know no one did it.
Okay.
No one somehow took the time to check the batching part and how we can do it. I've seen some work in KDD that did something smarter of how we batch and everything, but it's not based on virtual nodes or theoretically showing that it's a limitation or show that you actually lose information.
Gotcha.
But I really like the analogy to the LLMs part. So it could be very interesting.
Cool. No, I appreciate that there's some theory here. I feel like a lot of research is empirical and then you just call it a day. but
Yeah, I think it's both of them are pretty interesting. I lean towards the second part of doing theoretical stuff, then going to the implementation.
yeah.
I can assure you that not everything works. Sometimes it works in theory, it doesn't go, so you are just stuck. But
Gotcha.
when it works, it's pretty interesting.
Gotcha. Thank you.
Yeah, no worries.
Very nice. I think unless there are other questions, then I want to thank the speaker for showing up and talking about his work. It was super cool and super interesting. And thank you all for attending. And then I hope to see you again next week, where we have another really interesting session. So thanks everyone, and have a great Thursday.
Yeah, sure. Thank you.
You.
Bye.
Bye.
Bye.